Hey guys, welcome back. Today we're talking all about masses. To start off, atomic mass. So atomic mass is the number on the periodic table that's going to tell you how much an atom weighs. It's also called atomic weight, and it is taken in atomic mass units, also known as AMUs. So when talking about atoms, the number of protons and electrons vary, and the number of neutrons vary, and each of them adds weight to the atom. So when we combine all these things, we have to have a certain type of weight that gives us the specific atom. So for example, let's talk about carbon. If we're looking at the periodic table, carbon is number 6, and it's going to have a mass of 12.01. So 12.01 actually isn't the exact mass of carbon. It's actually the average atomic mass. So whatever you see here is going to be the average atomic mass. In the last video, we talked about isotopes, and isotopes, again, just to review, are going to be compounds that have a different number of neutrons. So we have things like carbon 12, carbon 13, carbon 14, stuff like that. And they're all going to vary. So the average atomic mass is pretty much if you took every single carbon atom in the universe and you averaged out the weights, that's the number you would get. So carbon 12 is the most common, and it has pretty much a mass of 12 AMUs. And then carbon 13 is about 13 AMUs. But carbon 12 is 99%, and carbon 13 is 1%, let's say. I don't know if that's exact numbers, but it's pretty close. Carbon 12 is going to take up most of that average, so that's why 12.01 is the average mass. You're never really going to find a carbon atom with a mass of 12.01, but if you're just assuming for carbon in general, you're most likely to find something in that 12 range. It's like if you average a test, like let's say 99% of the class got an A, one person got a 0, your average is still going to be really high, but there still is a chance that you didn't do well, if that makes sense. Whenever we're talking about atomic masses, there's going to be a huge variation of numbers depending on whatever compound it is, how much the compound weighs, how many isotopes there are, and just the dispersion of those isotopes. Like carbon, it's pretty, one obviously has the entire lump sum, but if whatever you see on the periodic table is going to be your average atomic mass. So with oxygen is atomic number 8, and it is 16.00. That's your average atomic mass. Hydrogen, it's 1, and I think it's 1.008. That's your average atomic mass. But yeah, whenever we're talking about atomic mass, it's important that we understand how to, unitize these things and how we can apply them to chemistry as a whole. So when we're talking chemistry, we need to have a set way to be able to apply certain values and ideas to. So let's think about baking. Whenever we have a baked good, such as donuts or cookies, we have a dozen of them. We always sell by the dozen or half dozen, whatever. But your dozen is your basic standard of identification for a set of cookies or a set of donuts. Whenever we're talking chemistry, we have what's known as a mole. And the mole, in this case, is our dozen. It's the set kind of value that we associate basic ideas in chemistry to. This mole comes from a guy named Avogadro, and he made this number. We call it Avogadro's number, and it's very important in chemistry. It is 6.022 times 10 to the 23. Very, very, very important. So this pretty much tells us how many atoms are in a mole. So if we're talking about a dozen, if we're talking like about cookies or something like that, there would be 6.022 times 10 to the 23 cookies in a dozen. If we're talking about carbon, there are 6.022 times 10 to the 23 carbon atoms in a mole. If we're talking about hydrogen, there's 6.022 times 10 to the 23 hydrogen atoms per mole. This number is your bread and butter in chemistry. So let's say we're talking about our atomic mass. Let's go back to that. So we said carbon is number 6, so 6 protons, atomic number 6, and has a molar or an atomic mass of 12.01, average atomic mass. So this atomic mass is actually also known as what we call molar mass. So our molar mass is how many grams are in a mole of a certain element or compound or molecule. So it's always going to be in grams per mole. Or you could do like that. Either way, always grams per mole. So if we're talking about carbon, for example, your molar mass is 12.01 grams per mole. Now that we have the understanding of what actually molar mass is, let's apply it to some chemistry. So when we're talking about molar mass and figuring out, what we need to do with that, we can apply this to different things. So we're not always going to have 1 mole of a certain substance. We're not always going to have certain things, right? It's always going to fluctuate. That's my point. Like certain things are going to weigh differently. They're going to be different weights. They're going to look different. They're going to have different shapes, different densities, everything. But if we're talking about, back to carbon, we'll stick with carbon. Well, let's say we have 6 grams of carbon. So 6 G's of carbon, 6 grams. We know, if we're trying to find how many moles we would have of something, that molar mass, which this is going to be in grams per mole. So at the start of this channel, there's a video on conversions, and we talked about something called dimensional analysis. So this is where dimensional analysis comes back into play. So we have 6 grams of carbon, and we're trying to find how many moles. So what we would do is we would do the molar mass of carbon, which is 12.01 grams per 1 mole of carbon. And we could do 6 divided by 12.01, and that gives us 0.49 moles. If we're looking at sig figs, there's one significant figure, 0.5 moles of carbon. So there's half a mole of carbon in 6 grams. And if we look at our molar mass of carbon, it's 12. Half of 12 is 6, we have half a mole. So you can kind of see where this applies. We can use anything to figure out how many moles. If we had 1,000,000 grams of carbon, right? We would take 1,000,000 divided by 12, and that would give you your answer. Let's talk about oxygen, for example. Let's say we have oxygen. So oxygen's number 8, and it has a molar mass of 16 grams per mole. So let's say we have 32 grams of oxygen. So we know if we have 32 grams of oxygen, we have our molar mass, which again is grams per mole. We want to cancel out the grams with the grams. So 16.00 grams of oxygen over 1 mole of oxygen, because again, we want our grams on the top and the bottom, so they can cancel out, same as we did here. Grams on the top, grams on the bottom. All we're left with is our moles. That's our answer we got over here. And over here, we're left with moles, so we're gonna get moles as our answer over here as well. So 32 times 1 is 32. Divide that by 16, that's 2. 2 moles of oxygen. And if we do the math again, we have 16 grams in a mole of oxygen. If we have 32, that's 2 moles. So again, it's applicable, we can use it. Now, let's talk about compounds where we have to, where we don't have this set molar mass, where it's not just showing us in the periodic table. So let's talk about carbon dioxide, CO2. So we talked in a video or two ago about molecular and empirical formulas. So CO2 is covalent, so it is a molecular formula. It's not going to be the simplest ratio, but we know that we have 1 carbon and we have 2 oxygens. So in a singular molecule of CO2, we're going to have 1 carbon atom and 2 oxygen atoms combining to make CO2. So when we're adding up our masses, we want to do the same exact thing. If we have 1 carbon, we get 12.01 grams per mole, and that's just by 1. We have 2 oxygens, so we do 2 times 16.00 grams per mole, and we take our 12.01 grams per mole, and then 2 times 16 gives us 32. Grams per mole. So now if we add up 32 and 12.01, we're going to get 44.01 grams per mole for 1 mole of CO2. So 1 mole of CO2 equals 44.01 grams per mole because we have 1 carbon and 2 oxygens. We took our 12.01 from carbon and we took 2 16s. We added them up, giving us 12.01 and 32, and we added those up, giving us 44.01, 1 mole of CO2. So now we can change this. We can throw this around. We can work this backwards. So let's say that we have, let's do 65 grams of CO2. And we want to figure out how many moles. So, again, we want to cancel out grams with grams and have moles on the top because, like we said before, all molar mass is in grams per moles. So grams are going to go on the bottom. So 44.01 grams of CO2 over 1 mole of CO2. Because we want grams to cancel out with grams. So we're left with moles. So our answer is going to be moles. Now, if we take this into our calculator and we go 65 divided by 44.01, we get 1.47 moles. But we want 2 significant figures because we have 2 numbers right there. So it's actually going to be 1.5 moles of carbon dioxide. So again, if we take 44.01 and we do 44 plus half of that, 22, gives us about 66. Pretty close to 65. Again, it's all conceptual. It's going to keep applying this way. It's going to keep doing these things. Now let's work one from behind. Let's say that we have let's say that we have 3 moles of carbon, and we want to find how many grams. So if we take our exact same thing, our molar mass, and we work it from behind, because again, it's grams per mole, and we want to put our moles on the bottom to cancel. So 1 mole of carbon equals 12.01 grams of carbon. If we multiply 3 times 12.01, we get 36.03 grams of carbon. So we pretty much did the exact same thing. We took our moles that we were given and we canceled them out with moles in the bottom, and we got 12.01 on the top because again, grams per mole, and we got 36.03. So 3 times 12.01 is 36.03. So for 3 grams or 3 moles of carbon, we know that each singular mole, so if we have 3 moles, 1, 2, 3. Each singular mole is going to weigh 12.01. And if we add all those up, we get that. So 3 moles of carbon gives us that answer. And let's do a bit of a harder one. Let's say that we have 5.6 moles of water, and we're trying to find grams. So it's a bit trickier. It's not just given to us in the periodic table. Let's go back. So if we're talking about water, we want to think about what is our molar mass going to be. So we have oxygen down there. It's 16 per mole. And hydrogen is 1.008, atomic number 1. That is what that's going to be. So when we're talking about water, we need to think of it like this. So we have 2 waters, so 2 H's, and 1 oxygen. So if we have 2 H's, we're going to have 2 1.08s. So 2 times 1.008 grams per mole, and 1 oxygen, so 16, or 1 times 16 grams per mole. So if we add all those up, we get 2 times 1.008, which is 2.016, plus 16, which gives us 18 points, and we want 4 sig figs, so 18.02 grams per mole for 1 water. Because we took 2 hydrogens, 1 oxygen, giving us 1 H2O. So 18.02 grams per mole is the number we're looking for. So as we've stated before, whenever we're doing dimensional analysis, we want to do top and bottom same unit. So we're going to have moles in the bottom here. So we have 1 mole of water, which equals 18.02 grams of water. So 1 mole of water is 18.02, because if we have a mole of water, we're going to have 1 oxygen and then 2 hydrogens. Hydrogen's going to weigh 1.008 for both, and then oxygen's going to weigh 16. We add all those up, we get 18.02. That's 1 singular mole. So we cancel out our moles on the top and the bottom. We're left with grams. So 5.6 times 18.02 is 100.9 grams of water. But if we're talking sig figs, we want 2 sig figs, so 1.0 times 10 to the 2 grams per mole of water. The sig figs here are a bit weird, but your teacher probably won't give you something like that. Don't get confused. 100 would be fine on a test or quiz. But yeah, this is your answer. If you want the exact sig figs, that would be it. But yeah, like I've said before, this is just going to be a practice thing. It's going to be getting comfortable with these values. Getting comfortable with dimensional analysis is going to be very important. This concept will come and again and again and again and again throughout chemistry. You're going to see it in so many different ways. Molar mass is going to become like, you're going to understand like the back of your hand by the end of the course. But yeah, I want to work through one more example. Something that used to always trick me whenever I was taking chemistry, and I think it's important that we kind of discuss it even for a little bit, just so you guys don't get tripped up as well. So for some reason, I just never could get across my head that this meant that there were 6.022 times 10 to the 23 atoms in a mole of something. So atoms per mole. And teachers will always ask, oh, if we have, 3 moles of hydrogen, how many atoms would that be? And I could never get this through my head. I don't know why, but I want to make sure you guys understand. So let's say that we have 3 moles of hydrogen, like we said, and we want to figure out how many atoms we have. So if we're talking about Avogadro's number, it's atoms per mole. So we want moles in the bottom. So we know that 1 mole of hydrogen has 6.022 times 10 to the 23 atoms of hydrogen. So if we multiply 3 times 6.022 times 10 to the 23, we get 1.8. We want 1 sig fig here, so 2. We're doing 2 sig figs, 3.0 moles. 1.8 times 10 to the 24 atoms of hydrogen in 3 moles of hydrogen. So we cancel out our moles, we're left with atoms, we figure out a number of atoms. And then same thing working backwards. Let's say we have, 10,000 atoms of hydrogen. How many moles would that be? So we know, again, 6.022 times 10 to the 23 atoms per mole. We want atoms on the bottom because we have atoms on top. 6.022 times 10 to the 23 on the bottom, because atoms cancel with atoms. Atoms cancel with atoms. We're left with 1 mole of hydrogen. 10,000 divided by 6.022 times 10 to the 23 gives us 1.7 times 10 to the 26 moles of hydrogen. So 10,000 atoms of hydrogen equals a huge number. But yeah, I don't know why this always messed with me on quizzes and tests, but it did. So I figured I'd share with you guys. But yeah, I'm gonna link some practice problems down below. Hopefully that helps you guys. But yeah, best of luck on your quizzes and exams, and see you guys next time.